Okay, so this is a short microphone test. Can you please check that the sound is okay and you can hear me well? Remote people are there? Yes? Wonderful.
Yes.
Okay, so then we start recording. Yeah. So in this second lecture, I want to introduce dynamic system models and how to simulate them. So before we optimize, we want to know how to simulate. And the lecture is first giving a little bit of an overview. And then we go from continuous to discrete time, a very important transition. I want to make some important remarks here, which might be less known in the computer science community. And then we go into real world issues, which are related to input-output models and stochastic models. After each of these sections, I want to make a short discussion break so that we can digest and interactively discuss. Yeah? So after each section, you can have some questions. I should say that some slide pictures were taken from other sources. So what is optimal control? It's the optimization of dynamic systems, and an optimal control problem is characterized by just 3 ingredients, I would say. Yeah, it's a dynamic system model, it's constraints, and it's an objective function, which might be a cost, as we say in MPC, or a reward in reinforcement learning, where we typically maximize. So it's just the same, just min or max. But let us focus now on the dynamic system model, which is the focus of this talk, only this. And if you think of a dynamic system model, we have somehow a function that describes the evolution of a system as function of a state, and the state we will call S in this lecture. And this state will come from some space, which we call also big S here, which might be in the real vector space or also in a discrete vector space for discrete systems, right? So, for example, games typically have discrete states, like chess, Go, and so on. Then we have a control action that is going from the so-called action space A. It could also be discrete in some cases. And then we have some form of random disturbance. I think we should also incorporate it here as a variable. Sometimes we will not use the variable epsilon later, but I think it's good to have in mind that very often we have some form of disturbance. For example, measurement noise, yeah? Or some state noise. And so let me give you already 2 important examples. The first one is a stochastic discrete time system. So here we would have an evolution function f that actually determines what will be the next state as a function of the current state, the current control action, and the current disturbance. Obviously, the disturbance is something we don't control, and typically this disturbance is stochastic, but it could also be an adverse player. Yeah? Then it's not a disturbance, but really a game, yeah? Someone doing something against us. For stochastic, we would say this is a random variable. I also want to point out at the bottom a dynamic system which is described by an ordinary differential equation. That's something that's most common in nearly all of physics and engineering, right? So we have a continuous right-hand side function, fc, I call it, this little index c for making sure that we distinguish it for continuous time, right? And here also we have a state s, but it's now a function not of a time index k, but it's a function of a continuous variable t. Well, the notation, we decided to put time index k as an index and call it k, that's discrete time. And when we have a round bracket with a t, then we say this is continuous time. That makes it easy to distinguish these 2 things. I will not show stochastic continuous time systems, which also exist, but they are clumsy and need lots of intricate notation, which we will not do in this course. So I will only look at deterministic continuous time systems, and these are so important that I want to dedicate quite some time to them. For them, I should say that we use a special notation, which is pretty standard. We denote the time derivative of a state by s dot. This is, I think, going back to Newton, even this notation. Then we often drop the time argument. We abbreviate s dot of t by the equation just below, S dot equals FC of S and A. Yeah, so we drop this time argument because it just makes our formulas lighter. And what Joschka and I decided in the upfront of this course is that we use the RL notation, which is state and action, yeah, SA. In engineering, lots of also numerical mathematics, people use X for the state and U for the control action. And then you would say X dot equals F of X and U, right? That's a standard term in control. And it might sometimes accidentally slip through my words or my slides because I'm more used to that, I should say here. Let me give you an example of an ordinary differential equation system. And for that, I need to fill up this bottle of water. Sorry. Okay, so I hope now that we can see here is a simple control system. Well, maybe I put the blackboard a bit higher. So that we can we see it better in front of the blackboard? I think yes, right? Okay. So here we have a system which has a control, namely my hand. I can move it up or down, right? And I have a state that is the position of this ball. No, it's not a ball, of this bottle, right? So let's say this upper position could be a thing that we want to control. I want to maybe move it to another set point a bit down, like this, right? That could be a typical control problem, or something up here. And I do it by moving this position, which I can perfectly control, but I cannot exactly control what's out here, right? And interestingly, there is another state. If you think of it, there is not only the position of this bottle that I need to know in order to predict the behavior of the system. I mean, there's something else, and that is the velocity of the bottle, right? So we also need to know the velocity of this bottle in order to describe its dynamics. So this system, we could just call a harmonic oscillator, a damped harmonic oscillator. It's a mass with a spring constant K. The spring constant is here. A friction coefficient beta, that is actually why this actually doesn't oscillate infinitely long. And then we can describe it by these equations that we have plotted here. X dot equals X dot 1 equals X2. X2 is the velocity, X1 is the position. Typically, we will only measure the position and not the velocity, right? And then the acceleration, which is X2 dot, is given by something that depends on the spring constant, and I can influence it with my manipulated variable U. What happens here? Why don't we see the screen anymore? Can you maybe see there? Maybe I didn't. It's back. Okay, good. Sorry. Yeah. And here you see now my old slide, how it was before yesterday with X. But of course, we modify it to the S and A notation, so we have the control action. Very often I say control action, yeah, to make both worlds happy, right? In computer science, you would just say action. In control, you would just say control or manipulated variable. So here we have a simple example for such a function FC at the bottom, just that you have an idea. 2 states, 1 control. Very simple idea. And I want to discuss some ODE examples with you. And for this, I want to go through these system ideas with you very briefly. And maybe we stop the recording for a few minutes and discuss that. Start the recording. Yeah. And now that we are a bit familiar with continuous time systems, I suggest that we think about how to go to discrete time. Because a lot of the work in machine learning and also in MPC at the end works with discrete time models. I think it's important to know how do we go from continuous to discrete time. And this is something that is a bit more intricate, I think, than sometimes people do it. So I should say that the main concept is already visualized here on the slide, and I think I need to somehow maybe make this disappear. Good. I call it the direct multiple shooting parameterization of a dynamic system. You can have many names for it. And it's a way to transform a continuous time system to a discrete time system by the following procedure. So you first decide to sample your state at discrete time points. That's like your equidistant time grid with a sampling time delta t. Second, you use a control that is piecewise constant. Yeah? That's just an assumption that's called zero order hold. There could be other parameterizations, but that's typically also implemented on digital controllers, and that's why we like this a lot. And then comes the key part, 3. We use numerical integration or numerical simulation to compute an ODE solution on these little trajectory pieces. Starting on the state S, it leads to the next state at the next time point. So this ODE is satisfied exactly on this sampling time, but the control is discretized. So the only error we make is actually this piecewise constant control, and that's also implemented in reality. So at this moment, we don't really do an error. Yeah? And we define then this discrete time transition map, which we call f of S and A, by the endpoint of the trajectory. This notation gets a bit clumsy because of this time grid and the lots of indices and so on. So let me just simplify this to the following. So we actually have this exact solution of the ODE. Conceptually, we start in a trajectory at the state S. I call the continuous trajectory X now, so I use actually this dichotomy of the two notations to our advantage. So the discrete time state is S. It's the initial value of that little problem, and the continuous state is X. This is then integrated with a piecewise constant given control A. And at the end of the integration, the state X at the time delta t, that's the output that we take. And then we have our discrete time system. It's as simple as that, right? So just a little integration. But then the question is, how do we do this simulation? And how do we do that in practice? And there are many possible ways. And the simplest way that I do not recommend, I should say, is a single step of an Euler integrator. Euler integrator goes back to Leonhard Euler, about 300 years ago nearly. And the idea here is just to take the state and go into the direction of our time derivative with the length of the time step. You can make this more accurate if you do more steps. So you could just do several of these steps. And here I introduce this index n, and then we have a loop that starts to do these steps. And each of the steps is then smaller. Now it's delta t divided by n. That would be already a bit more accurate. But it turns out to be very expensive, unfortunately. And there's a much more efficient way to get better accuracies even. And these are the higher order Runge-Kutta methods. For example, I give just one example. There is this Runge-Kutta 4 method that just takes the initial velocity. I call this V1, right? So the velocity at some point, at the initial point, I call it V1. Then I go half a time step into that direction and I evaluate my velocity at that point. I call it V2. I go another half step into this new direction, but starting from the initial point. So very funny thing, right? And then I call it V3. And then with this V3 direction, I go a full step and I call it V4. And then I weigh all these four velocities with different weighting factors, and then I get my F. It's for function evaluations, it's as expensive as 4 steps of an Euler. But what does it give us is much more accuracy. So if you look at a simple test equation here, that's just a mini system S dot equals S plus A, right? Simple system. One as a time step, starting condition S equals 1, no control, A is 0. And then we can easily compute the exact solution. So we have this exponential growth here, and at the end of the time interval, we get E. So the exact solution is here in black. The 4 Euler steps are denoted here. That's roughly how they look like. And you get a 10% error for this little example. One Runge-Kutta step does something magically. I cannot easily visualize it, but it nearly hits the point. Yeah? So that's what you would get here. It's 27 times more accurate than the Euler method. So I want to comment a bit on this field of numerical optimization. As I said, already 300 years old. And there's lots of techniques developed to accurately simulate differential equations. And there is a big family of methods called the general linear methods, as Butcher called them. And they can be divided into multi-step and single-step methods. And we are here mostly focusing on single-step methods. And there the Runge-Kutta methods are a very important family. And they come in two flavors, the explicit and the implicit variants. What all integration methods share in common is the integration order. And this order I want to explain on one slide. That also explains, as I hope, why the Runge-Kutta method of order 4 is so widely used, yeah? Which is puzzling, right? Why do people use this method among the thousands of different integrators? Why do they always use this one? Well, not always, but very often. So for each integration method, you have something that's called the integration order. I call it P. And you have another thing that's the number of internal stages, S, which is, for example, 4 in the Runge-Kutta method of order 4. For this method, by the way, it's accidentally P equals S, but that's not the case for other Runge-Kutta methods. So now you can always increase the accuracy by just doing more steps. Yeah? And then the total number of function evaluations is, I call it big M, which is the number of steps times the number of internal stages. Yeah? So if I do 2 steps of my Runge-Kutta method, I have 2 times 4, 8 steps, 8 function evaluations. And now it turns out that the integration error for these, for all these methods with a given order P is proportional to M to the minus P. Yeah, so the more steps you do, the smaller the error, obviously, but it shrinks with this minus P in the exponent, and that's the exciting part of it, right? So for small m, it turns out that low-order methods are most accurate. For example, the Euler method, which has just the order 1, is most accurate if you want to do 1 or 2 steps. Yeah? And the accuracy might be as good as 500% wrong, yeah? For example, or 100% wrong, something in this order. Typically, this isn't the order that we like as humans, right? So we want to have something which is maybe more like 10% accurate, or maybe 1%, or a bit better even. And that's where the higher order methods are getting more competitive. Yeah? And so the interesting thing is you can plot a kind of efficient frontier, as we might call it. So on the left, on the x-axis, on the y-axis, we have the integration error in a logarithmic scale, and on the right, we have the number of function evaluations, so like this number m, that is proportional to the effort of a method. And then for different methods, like the Euler method, the more steps you do, the better you get, right? So this is this order 1 growth, and due to this double logarithm, you see actually the exponent as a line. Here, the Runge-Kutta method of order 4 would be plotted here in purple, and an even higher Runge-Kutta method of order 8 would be plotted here. And it turns out that like at different accuracy levels, you get different methods that have the lowest computational cost, and this you would always prefer this method that's basically lowest. And you could do this with all possible integration methods for your example, right? And every example will look a bit different. But the interesting thing is that when you do it with lots of examples, typically the Runge-Kutta method of 4 is, so to say, the competitive method for 10% up to 10 to the minus 6 accuracies. And that happens to be the range of accuracies that humans like. Yeah? So I don't care if something is like 1 part per million wrong. I don't care. But if I do care if it's wrong by 10%. And that's basically the accidental reason why the Runge-Kutta method of order 4 is widely used. Yeah? It's just the cheapest method for human accuracies. And that's why we also use it a lot in this context. I wanted to actually give you one slide where you could, so to say, summarize all Runge-Kutta methods in a template that you could use for programming, if you like. So let me give you the general form of a Runge-Kutta method. Oh, this is not what I wanted. So if you look at the discretization equations for general Runge-Kutta methods, on the left is this ODE solution. that we want. And here I introduce already, just to make it a bit easier to remember what's happening in the Runge-Kutta method, I introduce this velocity already as a kind of algebraic variable, if you think so, right? So I reformulate my ODE with this V. Yeah, so V is just F at some point. And so that's just what we need to evaluate in this multiple shooting method, or in this way of discretizing our system. And on the discretized world of a Runge-Kutta method, you do n steps, and each of them has s stages, and then you start basically with a starting point, and you have these interesting transition equations here. You define at each intermediate stage the velocity, and then you add these velocities up in order to get another immediate state. And interestingly, this can be also implicit. So this is already covering implicit and explicit methods in one slide. And the crucial thing are these entries A and B. And they are what is called the Butcher tableau of a Runge-Kutta method. And if you know the Butcher tableau, then you know your Runge-Kutta method. And so you could just take any Runge-Kutta method of your liking. You take this template, and then you have your Runge-Kutta integrator. So I should say that we have two indices here. We have K for the integration steps, and I, J are for the intermediate stages, right? And you see, for example, that the intermediate stage X at the intermediate point I is given as a linear combination of all the velocities of all the intermediate velocities, so to say. Yeah, this is making it possibly implicit. So at the end, the complicated part is hidden in these two equations, and you have n of them, and each of them has 2 times s times ns equations. Ns is the state dimension, and you could potentially solve them. Yeah? So they have exactly the same number of unknowns. And you could solve that by Newton's method, or you can impose it as equality constraints in optimization. That's what we do in collocation methods, for example. So this is doable, but I just want you to note that this is like what's behind the numerical integration in most cases. And there is often an implicit solver needed. In particular, when you have stiff systems, you prefer these implicit Runge-Kutta methods, which are not like an explicit loop, but really you need to solve these equations. I give you 6 examples for Butcher tableaus. The Euler method I mentioned already. It has just one A entry, A11 is 0, and if something is 0, I just don't plot it here. In explicit methods, that's common. There is some tableau for the Runge-Kutta method of order 4 would look like this. And so you see also here all the diagonal entries A11 and so on, they are already 0 for these methods. That's what makes them explicit. So everything on the upper triangle must be 0, and then you have an explicit method. At the bottom, we have 3 implicit methods. The implicit Euler method, which just takes the derivative at the end, and better, more accurate rule that we call the midpoint rule, also Gauss-Legendre integration of order 2, or Gauss-Legendre of order 4, which is a 4th order method which only needs 2 state evaluations intermediately, and that's quite exciting, right? So you have only 2 functions, but you get the order 4. But you have to pay the price of an implicit equation system. But this is typically a very favorable method for optimization methods. And here at the left, I show just one plot which shows on one simple example. I think it's also a kind of oscillator where we did some experiments with explicit Euler, Heun, and Runge-Kutta 4. So just to show that I didn't invent the plot before. So here you see this efficient frontier, number of function evaluations as x-axis, and error at the end as the y-axis. And you see that basically nearly for all accuracies, you want to use this Runge-Kutta 4 method already. So we have reached an intermediate milestone, which makes us ready to start with a short break in a minute. So from now on, and throughout the whole course, we will not talk about continuous time systems. So please ask questions about them now. Yeah, we can maybe discuss some points later. But we will exclusively focus on discrete time models that we denote by this function f. And also here we can simplify notation by using this S plus operator. It's just making this simpler. I think it was invented by Jim Rawlings for discrete time systems, and I like to use it as well. So S plus equals F of S and A could be one shorthand for a discrete time system. And now to already focus our minds, what really we want to do in optimal feedback control and in MPC and RL in particular is that we want to design a map that we call a policy, which just maps from states to actions. Yeah, we call it pi. And this policy should make the closed loop system, which I put here at in the lower box. So the closed loop system is something that is just the state evolution under the controller, has desirable properties. So we want that this has, of course, respects constraints, and it might also, and it should also minimize some cost. So this is not roughly, this is in a nutshell what closed loop control is about and optimal feedback control's aim. So now there is a problem, and that is that in reality, this state is a very fuzzy object, right? So actually it's not unique. You might not be able to measure it. So it's something that is not really a real concept, but it's something that we invent in order to predict systems. And I would like to open the floor for discussion on this continuous time setting, and we stop the recording before we go on with the talk. And we would continue the recording. So, as we mentioned, the state is a quite artificial construct. And so there is a different class of models that we call input-output models. And I want to first take the input-output perspective on systems. And that's a more realistic perspective on a system. So typically we cannot measure what is called the state, and it's not unique. So what we really want is that a system model allows us to predict on a horizon that we call maybe length n, and a sequence of control actions. We want to know the sequence of measured outputs. Yeah? I think the index should start at 0. Sorry for that, for the control action. And then we also need to specify some form of initial conditions, for example, the initial state, just as an example. So this is like what an input-output perspective on a dynamic system is, and we don't care what's happening inside the system. It should just be able to predict, right? And there are two basic ways to represent deterministic systems with outputs. And the first one is building on our state ideas from before. So you can have a state space model with outputs where we introduce another function that we call G that could read out, for example, in our little case with this bottle, right? Think of this bottle. You would read out the altitude, the height of your bottle. Yeah? That could be something that you can measure, maybe even with a camera and some post-processing. This is then the only quantity that you know. So you could say it's partially observable. That's one name to give to this. But anyway, so with this quantity, you know quite a lot because you have time series of it. And then you still have the initial conditions. And for this bottle, it would be not only the measured position, but it would also be the speed, right? Obviously, you have these two states here. But there's also another perspective that we call the input-output model. And there we have to decide on an order n. Yeah, I call it n. And that is basically a time window of input-output pairs in the past. So you just remember the last n inputs and the last n outputs, and you predict the next output as a function of them and of your latest new action that you decide upon. So here the initial conditions are just the past y's outputs, right, and the past a's. I introduce now the y here, which is the output, yeah, of the system. That's typical in the control literature. I don't know if the output, the measured output, has a special name in the reinforcement learning literature, but I think that concept isn't so often used there, so I think it's okay to use the control language for the y here. And that is now interesting. Let's visualize what's happening here. So if you think of this recurrence equation, so we have to somehow find a function h. That's now our model basically, right? And this function h takes all the past actions on the window and all the past states on the window. States not, no. All the past outputs, the measured outputs on the window. And it takes our latest control action, one that we now can decide upon, right? In order to predict what will be our latest measurement. Yeah, so don't care about the index. Sometimes people like to prefer this yk plus 1, but I want to be consistent with the other system notation. So you decide on the A, and that A might directly influence your next your measurement at that time. That's what we call direct feed-through in control. But mostly it's influencing indirectly the next state only. So this is like creating a new type of state, and if you think of it carefully, then actually this past actions and past outputs, they are now the state. Yeah? And then you have nothing else than a state space model, and that's what we want to do explicitly here in this state space form of input-output models. And this is always possible. So if you have an input-output model, you can always transform it to a state space model following this procedure that I show here. So you just define the state to be all the past inputs and outputs. You can define the state, of course, not for 0, because you need already a window. So you can define it only for any n bigger than any k bigger than n. And then your state S is mapped to the next state S plus, and let's look into the details. So here we have Sk, that's the state at some time point, and it's mapped to a next time point. And this state is now actually a shifted version. So all the vectors are moved like down, right? And there are two new entries added at the top. One is our new y, and the other is our control that we introduce newly, that we can decide, right? And so that's this y is actually where our function h enters, and then we could just add our function h here, and that is creating our state transition map f. Yeah? So the state transition map contains the crucial part, the function h, and as a, let's say, less interesting part, it just shifts all the other states away and forgets some older states. So the oldest state here, this one here at the bottom, is forgotten. And then we have an output equation which would just do the same as this h. So that's here, you just read out the y, the new y. Sometimes I should say you can transform an input-output model, any input-output model that someone gives to you, you can transform, you can transform a state space model sometimes to an input-output model. That's not always possible, but it is possible, for example, if you have what we call observable and controllable linear time invariant systems. I will not go into detail here, just want to mention it. So you can also go from state space to input-output models in some cases, and that's sometimes useful. But it's not always possible. Just think of models without outputs. Yeah, if you don't measure something, you cannot transform it into an input-output model, but you could still maybe simulate it, right? Even without measuring something. Hidden dynamics, right? Yeah, what's happening inside people when they dream, for example. Okay, but this is already a bit too far from practice. I want to directly go to linear time invariant input-output models, which are very widely used class for also for linear model predictive control. And the main idea here is actually that you have this map H, as I called it before, is represented by a linear combination of the past measurements and the past control actions, and the latest control action enters via this term. So you always predict the next y based on all these numbers before, but now it's a linear combination. And I should say that these are sometimes also called autoregressive models with exogenous inputs, ARCS models. So if you hear ARCS model, then that's roughly what it is, typically with a bit of noise. Other people call them infinite impulse response models, IIR models. And that's due to the fact that if you make a step in your control, just an impulse, it would take a typically exponential decay for stable systems, but infinitely long after that. But now there is one special subclass when you set all these C components to 0, the ones that lead to the autoregression. If this part is absent here at the top, then you basically get the equation here at the bottom that is just making the next measurement depend only on the past inputs and nothing else, and on your current input. Yeah? So there's no memory apart from your past inputs. And that's called a finite impulse response model. And that's already covering lots of applications. I mean, a lot of models also in model predictive control are based on finite impulse response models with a little bit of recurrence. I mentioned it at the end of this talk. And there is also the contrary. When you don't have the B coefficients, you could have an autoregressive model which doesn't have an input. So that's this thing. You just say the next output is a linear combination of the previous outputs. Maybe one of the easiest and most famous examples for this type of system is the Fibonacci numbers. Maybe you've heard about the Fibonacci numbers. You start with 2 times a 1, and then you add the 2 ones to give a 2, and then you add the 1 here with the next 2, that gives a 3, and so on. So you have a moving window of size 2, and you always add the 2 last numbers, and you get increasingly bigger numbers, 3, 5, 8, 13, 21, and so on. And this is a very simple linear dynamic system, which is just autoregressive without an input. It's not useful for control, obviously, but it's just to give the idea of autoregression and what these models are. This, by the way, is an unstable system, right? It's growing. Its eigenvalues are, I think, related to the golden section, and unfortunately bigger than 1, which means they are increasing. So now that we have talked about input-output, which is a different perspective than state space, I want to go to the old examples again, and let's discuss, maybe we do this even while recording, what can be measured in these examples. Yeah, for example, if you have a pendulum, what could be measured? I mean, it could be just pictures by a camera, that would be one thing, but then it's a picture at one moment that doesn't reflect velocity, obviously, right? But still, it could be a typical measurement. A hot plate with a pot typically doesn't have a measurement, right? I mean, you can put your finger inside, you could put a thermometer into it, and then you could measure maybe the temperature in the water in the pot. That's not all the states, it's just the water in the pot. It's not the temperature of the plate, it's not the temperature of the pot itself. Continuously stirred tank reactors are a common process in the chemical process industry. Typically, it's just something like cooking continuously, so to say. You always put something into the pot, and you also extract something from your pot. And there you measure a lot of temperatures, typically, sometimes a bit of concentrations. Typically, these concentration measurements come with a delay, I mean, of a few minutes or sometimes longer. Think of PCR tests for corona. Yeah, so they take a delay of 1 day, typically now like 1 hour. And in chemistry, we have also some sensors which take like a longer processing time. But you never measure everything inside such a reactor. Robot arms, you would maybe have a camera watching them. Maybe you have sensors that encoders that know the angles of your joints. For moving robots, yeah, there it's really interesting because usually they have the self perspective only, so they might know some waypoints or maybe some camera images on their own. The same for race cars and airplanes. Yeah? And for these applications, we typically also have GPS that helps us to know a bit where we are, or not a bit, it's very useful. Yeah? But we typically, for example, for an airplane, there would be no direct sensor that tells you in which orientation your airplane is, right? So this one you can only infer from measurements of your IMU, maybe from knowledge about your trajectory and so on. So just to get some examples. So this is all I wanted to say about input-output models, and I still want to have a short interactive session now, so we could stop the recording for a moment. Models. So last part of the lecture is about stochastic system models, and in reality we should know that we always have some random noise. I call it epsilon here. That could be disturbances, something like unmodeled things, and also measurement errors, which are nearly always present, right? And I should also say that we typically have some unknown but constant system parameters. It could be all the parameters of your model, but it could also be some things that we think it would be important to know. Let's say in a car, you're sitting in a car, you want to control the car, and the car has a certain weight, but this depends on the number of passengers in the car, right? And that is roughly constant, at least during the driving. But it's something that you might want to estimate, maybe even online, right? So the mass of the car. And these are like constant system parameters, and they all influence the output. I should say that these parameters are conceptually not so different from states, and sometimes we just use a very simple trick. So we just say parameters are some states that stay constant. So they obey the dynamics pk plus 1 is equal to pk. Yeah? And they might drift if you add a bit of noise, and then you can estimate them with state estimation techniques and so on. So in that sense, notationally, we will usually not have parameters here, but it's important to keep in mind there are parameters that we just think to be constant during the time of our control action. So now I want to go into stochastic state space and also input-output models, and they are just a bit different. And the most general form is on the left. So on the left, we see some random variable epsilon k, and then it somehow influences the state transition. So the next state is influenced by noise, but also the measurement is influenced by noise. And it might be influenced by the same noise or by different noises. On the right, I already show a special case, and that's like the most common one, where we have a so-called state noise added to the state here. Sometimes not all states are uncertain. For example, typically the derivative of the velocity, the derivative of the position is always the velocity, so you wouldn't add noise on that, right? But you might add noise to other equations. But this is like the most general form, just additive state noise, and additive output errors or measurement noise is something that we will nearly always have, right? Every sensor has some reliability. So that could be an example. And on the stochastic input-output model, we would just say the next output y depends typically here on a window of the past noises, right? So we have this n also for the noise typically. And one of the simplest noise models is that you just have additive noise to a deterministic equation, and then we call this model assumption equation errors. And that's something that's very widely used, I think, in both system identification and also basically a good assumption maybe for a black box model that you identified with a neural network. You train these residuals, so you basically minimize these equation errors, and this gives you some form of also stochastic view on your predictions. So you know that your predictions will be disturbed by some form of noise, and you assume this noise to be just additive on the y. I want to point out one little difference. I mean, you might think that output errors like here, they affect the y, right? And here we have equation errors, they also affect the y. So maybe they are the same, but in fact they are not. Yeah? The difference is that here, the state itself is unknown, the s. Yeah? And these output errors don't affect the state dynamics at all. While here, they go into the auto-regression, because the next time that this function is called, the y that we just disturbed by noise is now entering our function. So there is auto-regression, and our noise is in fact a mix of state noise and equation error and output noise. So these equation errors are really disturbing our state, because we assume that the y is the state. The measurement is noiseless, so to say, but it's uncertain and disturbed. But when we measure it, we think this is the right measurement. It's different than output errors. Okay, I should say, and this is one thing I want to stress, that if you want to implement an MPC controller, which is certainly model-based, you need to address two tasks. And the first one is system identification, which happens offline. That means before you deploy your controller. That is typically using a long sequence of input data and output data that typically are specially designed, so like excitation experiments and so on. These are like identification campaigns. Huh? So some engineers visit your machine, your plant, and they excite it and they record data, they go home, they process it, and then they tell, this is a good prediction model. And there you can use techniques like least squares optimization, or in linear systems, there's a beautiful method called subspace identification, where you, so to say, identify the order of your system and the matrices simultaneously with very elegant techniques. After you have your model, then you go into the actual controller, but also here, because MPC needs a state, it first needs to estimate the state. And so we have state estimation, which is happening online. So when we have the state sk in the future also, we will talk about the state s all the time, but this needs to be estimated in reality, at least if we have stochastic models with output errors, for example. And you do so by using all the past data that you have until k-1 and all the past measurements that you have. And then you can do this recursively by techniques like the extended Kalman filter, very widely used, or for linear system, just the Kalman filter. You can also use what we call moving horizon estimation, which uses a fixed window of past data for fitting a simulation model. It's a bit like system identification, but your parameters are now fixed, and you just play with the initial value of your simulation horizon, which is now a free variable, and that fits your data, and you're most interested not in the initial, but in the end value of your fitting window, and that's what you call then the state estimate. Okay, so that's roughly state estimation. And if you talk of learning-based MPC, yeah, that's something where we typically refer to an online model adaptation. I mean, there are other forms, but typically people think of online model adaptation. Sometimes you could, in the past, people call this also adaptive control. But so the main point is that we would also estimate parameters online, not only the state, but also parameters which we think are changing slowly and for which we don't have dynamics typically. And I claim that moving horizon estimation, because it's a nonlinear optimization-based technique, is particularly suitable to this model adaptation. And just for the vocabulary, I think we always should clarify the different languages. And if you say learning a model in machine learning, then in control engineering, you would say system identification. And it's, I think, really the same thing. So it's good to know this vocabulary. And I try now to somehow make a relation to Joschka's language. So in some sense, we need this whole topic of state estimation only if we have what we call partially observable Markov decision processes, POMDP. And so let me just try to make a bit of a link between these two worlds. So there is basically a fully observable Markov decision process is one where you observe the state. And the partially observable one is where you don't observe the state, right? And from the left perspective is the state space view, everything state space here. I just showed what I've shown before, right? That's a partially observable system because you don't know the state. You cannot measure the state. You can estimate it, but it's not fully observable in this language. But if you can measure basically the full state, if you know the Y, then you have a fully observable MDP. Yeah? And for input-output models, this is always fully observable by definition. So that's the beauty of that. In Joschka's talks, you will very often use a different language. So we will not use this noise epsilon. Yeah? So there, Joschka talks more about probability densities, or in discrete state spaces, even probabilities. I have here the continuous view, so I talk about probability density functions. So your system is basically, once you have identified your system, it's characterized by just the transition function from states and controls to the next states. And so this is a conditional probability. How likely is it that this next state will be at that value or at that value, given my initial, the starting state and the control. And also the measurement is some random variable that for which I might know some distribution. Yeah? So in a case of additive noise, this would be just a deterministic measurement plus a Gaussian, for example, right? And a fully observable, yeah, in this language would just be, as I said, one where the probability density of the output, the thing that you measure, is, so to say, perfectly known. I mean, the only output that you can measure is the right state, and all other things have probability density 0, so they will never be measured. So you have just exactly, basically it's an expression of that quantity here, right? So you measure the state, that's it. So just a trial to do a bridge. And so now the beauty, as we have already seen in the discussions, is that input-output models don't need a state estimation. They are automatically, so to say, fully observable in this MDP language. You need to decide on an order, and it's a strong assumption, obviously, that this is the case. But once you have made this assumption, your state is just given by this past inputs and outputs, as we have said before. And then you can use these models, for example, in what is called end-to-end learning. You just take the last 10 pictures and you decide on the next action of some controller, for example. I should say that these input-output models are also used in some linear MPC implementations. And one typical implementation that I've heard many practitioners like to use is this little, it's an ARCS model, but it's based on a step response model. So you basically say, you identify first step response, yeah? you say, oh, my y depends on past actions in a linear form, so it's a weighted sum of past actions. But then you know, okay, the y also has some memory, and if there's an offset, then I should know about this offset. So you basically subtract the mismatch of your linear FIR model from the past measurement, and then you use this for a correction of your next output, so to say. All right. So this is, so to say, it's derived from an FIR model, but it's autoregressive. You could say there's some uncertainty, then you get these equation errors. And this model is used in lots of MPC applications. Just the only thing you have to identify are step response coefficients. So it's relatively easy. With one single experiment, you switch on a control, and then you get the B coefficients. I should say that also in nonlinear black box MPC or model-based reinforcement learning, you would use input-output models very often. We mentioned that already, that you could use a neural network to represent this mapping H. Deep neural network, very nonlinear in both states and parameters, but extremely powerful to represent possibly very intricate systems. So let me summarize this talk on models. So first, let's distinguish the different classes, and we all should keep in mind that the continuous and discrete state space and controls. Today I talked mostly about continuous state space, but when we look at games like chess and Go, there are discrete states, right? We have continuous time versus discrete time, and we now know that we can just transform one into the other by this multiple shooting idea. And then we can continue to talk about discrete time systems from now on, and that's what we will do. You have linear systems and nonlinear systems. I didn't focus too much on it, but it was implicit in many of the discussions, right? Linear systems depend linearly on the actions and on the initial states. Then we have state space and input-output models, very different approaches that can be transformed. Input-output can be transformed to state space always, the other way sometimes. We have deterministic models, which are typically more easy to imagine and related to the physics. And then we have stochastic models, which are very useful in all contexts where we can't perfectly model. And we might have fully or partially observable systems. And this is something which I shouldn't say the good conscience to control engineers, because there is, in fact, the notion of observability, which I didn't talk about today, which is a bit related, but not exactly, not the same as a partially or fully observable system, right? So actually, I should say that a partially observable MDP can have an observable system model at the boundary, at the bottom. And observability meaning that from measurements you can estimate the whole state. And some systems you can do that, in others you can't. But so please distinguish this systems theory observability notion. So I said already that we can use numerical simulation, and I've shown this one slide on the Runge-Kutta method. Please remember that. Take your tableau, and then you know how to simulate, right? And in the sequel, we will use these two notations. For deterministic systems, I like this S plus equals F of S and A. Yeah? And for MDPs, we will very often use this more probabilistic point of view that S plus is somehow conditioned on the S and on the A. And we have the state in state space and control in action space. So this is like what we will use models for, and the next talks will focus on more constraints, on optimization, on how to design the controllers, but they will all use this notation of systems. And so we thought it's good that we start with systems at the beginning of this school. Thank you very much for your attention. Now I think we still have some time for questions. I mean, we are exceeding our time budget significantly, but yeah.